In this video, we're going to be tackling the LeetCode question, maximum depth of binary tree. Now, I'm assuming that you have at least a vague idea of what a binary tree is, but if you don't, let me fill you in very quickly. A binary tree is just a data structure that looks like a tree. But where does the word binary come into play? It's called a binary tree because of the parent-child relationship. If you notice here, we have one parent, and we can have between 1 and 2 children underneath this parent, hence the name binary. But what exactly is the depth of a binary tree, and how exactly do we find this depth? The depth of a binary tree is very similar to the depth of a pool. If we want to find the depth of a pool, we start at the top and we work our way down to the bottom. A binary tree is no different. We're going to start at the bottom and we're going to work our way down to the maximum depth. And in our case, this number is going to be 3 because there are 3 nodes on our way down. How exactly are we going to create an algorithm to do this, though? What we're going to use is we are going to use the easiest algorithm of all, the depth first search. And you guessed it, depth is actually in the name of this algorithm, so this is going to work out perfectly. The depth first search algorithm is, you guessed it, optimized for depth. It is optimized to find the deepest part of the binary tree as quickly as possible. But there is one huge caveat, and LeetCode mentions this in the description. The depth first search recursive version is going to be too easy for most interviews. And this is the reason that we're going to have to use a stack. We're going to have to use the iterative version. So here's how this is going to work. So first things first, we are trying to find the depth, so we are going to create a variable that's going to store the depth for us. Second thing, because this is an iterative depth first search, we're going to also initialize the stack to store where we are at within the binary tree. And lastly, what I'm going to do is I'm going to provide a little box for us that's going to show the pointer or the place that we are at within the actual depth first search. So the very first thing that we're going to do before we do anything else is we're going to add the root node to the stack. We are also going to increment the depth. Once we get done with those two things, we're pretty much done. We can pop the root node off the stack and we can add our children nodes, which are going to be 9 and 20. Because it's a stack, 20 is going to be next, so we're going to repeat this same exact process. We are going to increment our depth. We are going to pop 20 off the stack, and we are going to search below us for children nodes. We're going to check 15, and we're going to also add 7 to the stack, and we're going to repeat this same exact process. We're going to move to 7. We're going to increment our depth. And because we don't have any children underneath, this process is going to be very simple. We can pop 7 off the stack, then we can move to 15, and this process can be repeated. But it's going to be a lot easier because we don't have children. Also, because we haven't exceeded the depth of 3, we're not going to increase our depth. We'll go ahead, pop this off the stack, move to number 9, and repeat the same exact process. We have no other children. Our depth has not exceeded 3. We can go ahead, pop 9 off the stack, and we have traversed the whole entire tree. And that's how it works. So let's go ahead, let's hop into IntelliJ, and let's code it. So first things first, let's go ahead and create a Java class, and we're going to call this tree node. It's good to build these tree nodes to see how the actual data structures work, and it's super easy to do with AI. So we'll have tree node left, we'll have tree node right. We will also create an empty constructor. Let's go ahead, just create an empty constructor. Then what we'll do is we'll have a constructor that passes in the val, and we'll set this to this dot val. We'll go under here, we'll say public tree node we'll have the val, we'll have the left and the right node, and we'll go ahead and set the this for each property. And that's pretty much it. So let's go ahead inside of here. Let's create another Java class, and we're going to call this solution. So the first thing that we're going to do is we're going to create a little helper object, and this helper object is going to be called node depth. And the name node depth is very appropriately named because it's basically just a tree node with a little backpack on it, a little data backpack that's going to keep track of the depth. So we'll say tree node, and this tree node is going to have the depth attached to it. And the reason that we need the depth attached is because as we traverse through all of these levels in this tree, if we change levels, there's a good chance we could lose the depth. So we need to keep track of the depth with the actual node in the stack. Once we get the node depth built, what we're going to do is we're going to actually build the algorithm that LeetCode wants, and we're going to call it max depth. So before we do anything else, let's just do a really quick edge case check so that we look good in front of interviewers, as well as make sure that we don't kill our algorithm's speed. Because we're returning the max depth, what we're going to do is we're just going to create a little piece of state, an integer variable, to store that for us. Also, because this is a depth first search algorithm that's iterative, we're going to be utilizing a stack. And within this stack, we're going to be housing individual elements of our node depth object that we just created. And let's go ahead, move on to the next part, which is going to be adding the root element to our stack. Now the AI is going to try to add 0, but we want to add 1. And we also want to go ahead and add our root to the node depth. Now we can finally move on to the good part, which is iterating. So while we are iterating, the very first thing that we always do is we pop the first element off the stack. Because this node depth has 2 pieces of data on it, we're going to go ahead and we're going to destructure it. We're going to take those pieces of data out and we're going to turn them into variables that are going to make more sense. The first one is going to be the current node, and the second one is going to be the current depth. So each time that we iterate, each time that we visit a new node, we're going to determine if that new node is the maximum depth. And the way that we do that is we compare the maximum depth to the current depth, and we take the math.max to determine the new maximum. After we get done doing that, what we do is we check below. Do we have any children beneath us? And if we have children beneath us, we're going to go ahead, we're going to add them to the stack, and then we're going to do the exact same thing for the right. Once this gets done iterating, we're pretty much done. And once we get done iterating through everything, what we can do is we can return the maximum depth. So what I'm going to do is I'm going to go ahead, get out of full screen mode here. And I'm going to copy everything within the maximum depth, and I'm going to go ahead, put it in the LeetCode editor. So I'm going to go ahead and LeetCode. I'm going to toss that into the max depth function. Now what I need to do is go back and get my node depth class, helper class that I created. I'm going to do the exact same thing. Go ahead into here, put this within the solution. I'm actually going to move this over, make it look a little bit better. Let's go ahead, run, see if our test case is passed. Congratulations, our test case is passed. Thank God. Let's go ahead, hit that submit button, and let's see our time and space complexity. So our time complexity is n, and our memory is n as well too. Anyways, hope that you guys enjoyed this. If you did, make sure to smash that like button, smash that subscribe button, and as always, thank you for watching.